What specific problem does your proposed framework transformer $2 and singular value fine-tuning (SVF) aim to solve? Can you describe the challenges in current LLM training methodologies that motivate this research?
The proposed framework transformer squared and singular value fine-tuning (SVF) aim to solve the problem of achieving self-adaptive large language models (LLMs) that can efficiently adjust to various tasks and dynamic contexts in real time. Current LLM training methodologies face significant challenges, including the resource-intensive nature of traditional post-training, which often leads to high computational costs and long training times. Additionally, these methodologies struggle with performance trade-offs when broadening the data, resulting in overfitting and task interference. SVF addresses these issues by providing a parameter-efficient fine-tuning method that focuses on tuning only the singular values of weight matrices, thereby reducing computational demands and mitigating overfitting risks. Ultimately, Transformer Squared enhances this by enabling dynamic composition of expert modules, allowing for continual learning and adaptation without the need for constant retuning.
Can you explain in detail how the SVF method works, including the step-by-step process from the initial weight matrix decomposition to obtaining the modified weights for the LLM?
The singular value fine-tuning (SVF) method operates by first decomposing the initial weight matrix, W, of the LLM using singular value decomposition, SVD, yielding three components, W equals U sigma V caret T, where U and V are semi-orthogonal matrices and sigma contains the singular values. The next step involves learning a simple vector, Z in math BBR caret R, that modifies each singular component of W independently, resulting in a new weight matrix W equals U sigma V caret T, where sigma equals sigma O times text diag Z. This parameterization allows for efficient fine-tuning, as it requires learning only R parameters, significantly fewer than traditional methods like LoRA. The learned Z vectors provide targeted modifications to the singular values, enabling the model to adapt to specific tasks while maintaining the original model's expressiveness. Finally, SVF is trained using reinforcement learning (RL) to optimize task performance directly, allowing for effective fine-tuning even with limited data, thus enhancing the model's capabilities without the risk of overfitting.
Could you provide a concrete example of how the two-pass inference mechanism of transformer $2 operates? Illustrate this with specific values or scenarios to demonstrate the interaction between the expert vectors and the adaptation strategies.
The two-pass inference mechanism of transformer squared operates by first executing the model to observe its test time behavior and gather relevant information about the task at hand. For instance, consider a scenario where the model receives a prompt related to mathematical problem solving. In the first pass, the model identifies that the task requires skills related to arithmetic and selects the corresponding expert vector, say, Z caret 1, which was fine-tuned on a dataset like GSM-8K. This expert vector is then adapted to create a new vector, Z, tailored to the specific conditions of the task. In the second pass, the model uses this adapted vector, Z, to modify its base weights and generate a response, effectively combining the capabilities of the selected expert with the base model's knowledge. This interaction ensures that the model dynamically adjusts its behavior based on the task requirements, leading to improved performance in solving the mathematical problem.
What empirical benefits were observed from using SVF compared to traditional fine-tuning methods like LoRA? Include specific metrics or performance improvements noted in your experiments.
The empirical benefits of using singular value fine-tuning, SVF, compared to traditional fine-tuning methods like LoRA were significant. In our experiments, SVF consistently outperformed LoRA across various tasks and models, demonstrating considerable performance gains, particularly in the vision language domain where SVF improved the base model's performance by over 39%. Additionally, SVF required less than 10% of the training parameters compared to LoRA, highlighting its efficiency, while LoRA experts yielded smaller gains and even sporadic performance degradation. SVF maintained stability and effectiveness, particularly in tasks with limited data, as it mitigated the risk of overfitting. Overall, SVF's parameter-efficient approach and principled regularization led to superior task performance, validating its advantages over traditional methods.
How did you validate the effectiveness of the transformer $2 framework? What datasets, experimental designs, and performance metrics were employed in the evaluation process?
We validated the effectiveness of the transformer squared framework through extensive experiments across multiple tasks and models, specifically assessing the efficiency and effectiveness of the singular value fine-tuning (SVF) method and demonstrating self-adaptiveness through 3 proposed adaptation strategies. We utilized 3 pre-trained LLMs, Llama 3-8B Instruct, Mistral 7B Instruct VO3, and Llama 3-70B Instruct, training SVF vectors on datasets such as GSM-8K, MBPP Pro, and ArcEasy. The experimental design included evaluating the performance of Transformer Squared on unseen tasks like Math, HumanEval, Arc Challenge, and OKVQA, comparing it against traditional methods like LoRA. Performance metrics were based on task-specific accuracy and improvements in model performance, with results indicating that Transformer Squared consistently outperformed LoRA, particularly in self-adaptation scenarios. Additionally, we conducted ablation studies to analyze the contributions of different components and adaptation strategies, further validating the framework's robustness and adaptability.
What do you identify as the primary limitations of your approach with Transformer $2 and SVF? And what suggestions do you have for future research directions to address these weaknesses?
The primary limitations of our approach with Transformer Squared and SVF include the increased storage and computational demands associated with fine-tuning multiple expert modules, the risk of overfitting when training on smaller datasets, and unresolved challenges in the flexible composition of expert modules. Additionally, while SVF significantly reduces the number of parameters needed for fine-tuning, it may still face issues with sparse rewards when the base model is weak, which could hinder performance. For future research directions, we suggest exploring more efficient methods for managing the storage and computational costs of expert modules, developing techniques to mitigate overfitting in narrow task domains, and investigating advanced strategies for the dynamic composition of expert modules to enhance adaptability. Furthermore, examining the transferability of SVF-trained expert vectors across different model architectures could provide insights into improving the scalability and generalization of self-adaptive LLMs.